So next we have Jannick Bendtsen talking to us about PipeBio.
Thanks a lot. So this will be extremely fast and extremely high level, but you can go down and talk to Owen at the booth after this, or you're also welcome to sign up for a free trial online. We'll intercept all your emails and we'll be in touch directly if you sign up. Nevertheless, what I'll be talking about today is basically to showcase our platform. And basically the question is, how fast can we find potential antibodies in the paper that I'll just show you in a second. Basically to replay the experiments they had in the paper and how fast we can do that. So we have a sequence agnostic bioinformatics platform. So we support from MySeq all the way up to NovaSeq. We have customers regularly running more than 1 billion sequences in our platform. We of course also have support for PacBio, so long reads, but also very commonly used Sanger data. So the paper that I was referring to is the paper from Henke et al. So in the beginning of the pandemic, they raised nanobodies against SARS-CoV-2. And here we'll just show how fast can we actually, or can we find the same sequences that they found, and how fast can we actually do that. So what is PipeBio? It's a managed cloud platform for bioinformatics, sequence analysis, primarily focusing on antibody discovery. And we're the first ISO 27001 compliant discovery platform. So just a bit on the user interface. So this is a document-based system. So whenever you upload one FastQ file or one sequence, you'll have on the left-hand side, you'll see that you'll have one document in here. So it's exactly the same as a Word document or an Excel document. So very easy to use. In the top menu, we have you have access to all the tools. So that's around QC, of course, 10x QC, Sanger QC for secondary peak detection, and so on, and also all our analysis tools. So the annotation part of the pipeline, the clustering, the alignment, the differential enrichment, and so on. So all the tools are available there. The rest of the user interface, you'll see on the lower half of the screen. You have a tabular view together with a sequence view. And the upper half of the screen, you have a graphical view where you can show charts, which are all interactive. And in this screenshot, we also have a list of potential liabilities found and errors found in the data. So that's stop codons, frame shift, and so on. So basically, the task here is to create a project, import and QC the FastQ files, run the annotation workflow, and then find the enriched sequences in the Tyson data. So first, we just create a project, and we assign who are users on that project. We import the FastQCs by simple drag and drop. So we focus very much on the end user. So this is not a bioinformatics platforms where you need to know R or Python or anything. It's all available through the interface. So just import your FastQ files by drag and drop. In this data set, we had nearly 11 million paired end reads. And there's just an overview of the 4 different samples, how many reads are in there, and also a graphical representation of some manual QC we have done. So after import, we have just ran a workflow where we merge the paired end reads and annotate that. And that takes less than a couple of hours in this case for these 11 million reads. Just one of the results on the merged FastQ files. So again, as you saw in the other overview, we have a representation of how well the annotation process went. And all of these charts and graphs are interactive. So you can click the green area to filter for all your correctly annotated sequences. And at the same time, you have a list of all the problematic sequences where you have frame shifts, insertions, and so on, stop codons. Along the way, we have a number of summary documents, so you can actually see how well the merge and the annotation process went throughout the process. So now we have merged the paired end data, we have annotated all the sequences, and now we actually want to set up the comparison document, or comparison, where we actually have the library and we have the two panning rounds. After that, we run a differential enrichment, and the output of that is a volcano plot where and you're well aware that on the sort of upper right corner here, we have the most enriched sequences based on fold change and statistical significance. And luckily enough, the one which is highlighted here in the very top right corner is the same sequence as they found in the research paper. So it's the most differential enriched sequence, and we picked that one as well, which is lucky, I guess. So just a bit more on sort of the summary here, just counting how many times we actually found the exact sequence. There's also a view here on the alignment we actually did at the end, where we also aligned to the IMDT numbering scheme. So that's why you see the sort of the tract in the alignment on the CDR-H3 region. So we went from 11 million reads down to 8 representative sequences, and it's all basically done in less than a working day. And you see the time to actually compute this here. This is highly scalable, so the customers we have which are running NovaSeq data is actually able to do sort of similar approach, but in less than a couple of days for more than a billion sequences. The platform can do a lot more than just this. We also have support for batch restriction cloning. You can do other advanced workflows. You have the ability to do analysis of different scaffolds, so that being FABs, SCFVs, full IgGs, etc. You can actually edit your sequences in here. And of course, you could also add your functional data, so ELISA data or binding data to your individual sequences as well, and use that to also mine your NGS repertoires. We have other tools for library design, finish maturation, and of course, for the bioinformaticians here, this is all supported by an API, so you can also make your own integrations to other tools or use that to upload your data. So please come by the booth, and that was it. Thank you.
Have we any questions for Jannick? I'll ask the first one to get us started. You mentioned that you can upload assay data and use that in the platform as well. What does that look like? How does it function?
So typically, assay data comes as numerical values, and it's typically not done on NGS, but more on Sanger based. So if you have a plate of Sanger sequences, you will actually have your ELISA or your HEC titers, and you can just associate that per sequence, basically.
Great, thank you. Any other questions for Jannick? Right, thanks very much, Jannick.